When you come Is it a pop-out window? Okay. Alright. Go ahead and kill the music for now. Josh is in there. Okay, hope you guys enjoyed my royalty-free music session. Josh, if you wouldn't mind, could you give me an audio sample now? Can you tell me how I'm doing? Should be coming in clear now because I was talking to Colonel Sneed in the hallway. We're about 2 minutes away from officially beginning. And again, this is going to be recorded or saved to the YouTube channel. So if I get ahead of you on something or if you fall behind, just go ahead and rewatch it a couple times. Was Ruben coming in today? He's not. So we have Josh. We have Sean the pet attorney. We have Tommy, it looks like. And of course we have you. You think I'm ready to go? Ready to begin there, bud? Alright, so I'll start kind of talking through what you're seeing on your screen. For those of you that have been in the lab, the table of the work surface should look pretty familiar. It's the exact model of the spoil board that we have mounted on the Monster CNC machine. So you'll notice, for those of you that haven't seen the CNC work table just yet, it's got several holes. So we have these ones right here that have the mounted slots in it. These holes here, these are the holes that actually attach the spoil board to the table. These other circular holes that are off to the side, these actually did not cut out in our spoil board. I left those out. Those are for bench dogs, and when we do the surface or the spoil board once more, I'm actually going to include those in that that new one, just because some people might like bench dogs and some people might like the other method, like the bar clamps here. We typically use these bar clamps, which are these blue items here sticking through the table. We typically use those to secure the workpiece to the spoil board. I've got these in simulation mounted in a certain point. It'll make a lot of sense to you here in a minute when I actually go through and create a setup. Alright, so the fundamentals of CNC, right? The table's set up in such a way where the cutter moves on 3 axes: the x-axis, the y-axis, and the z-axis. If you look in the top right corner of the screen here, you should see a red line, and it's got an X right next to it, and then a green line that has a Y right next to it, and then a blue line that has a Z on the top of it. And then you have your front side, your left side, your top side, and of course if I were to rotate this view around, you have your right side, your back side, and your bottom. Alright, so what our goal here is today is to use the CAM section or the manufacturer section of Fusion 360 to create a toolpath that will cut out a part. Now, the milling operations that we're going to be carrying out today are basically two-dimensional. I wouldn't even go as far as to say that there is a 2.5 or well, yeah, I guess you could say 2.5, because we're going to be traveling on the x-axis, we're going to be traveling on the y-axis, and we're going to be traveling on the z, but we're not doing any difficult shapes here. And by difficult, we don't have, like, we're not cutting out, for example, a rounded object or like a half of a circle. If you were to take a sphere and cut it in half and stick it on this table and use CAM toolpath, that would be like a full 3D toolpath. We're not doing that today. We're going to be using only the 2D toolpaths, but we're going to be traveling in the Z direction. So I think some people would call that a 2.5D, but let's not get too hard into semantics. Let's focus more on the technique. So the file that's on the workbench today is a very dumbed down version of a file that I had seen floating around in an email coming from Sean, the patent attorney. So I took the same concept and I made some basic shapes that I can use to show a couple of pockets, some issues that you run into when using a CNC machine and end mills, and yeah, basically I think I've got it all covered there. Alright, so let me go in here, and I'm actually going to hide a couple things just so that we can let's see here. There's something I gotta get rid of. Alright, so let's say this was your resulting piece. This is what you wanted to pull off at the end of the day. Perhaps in this case you would go and stain it or sand it and do something with it, right? So you would model this in CAM, you would model this in the CAD side. So let me just switch back to the design and we'll hide some of these components here. So you would model this out in CAM, and then sometimes what I think is a good idea is to take the final result and then also design the stock that you're going to cut it out of. So this bigger rectangle here could represent the stock that I was going to cut it out of. So let's say, for example, I had a piece of 3/4 inch mahogany, and I want to make this final part right here out of that mahogany. You're going to want to cut a big enough piece of mahogany that you have some extra material on the sides of it in any of these directions, and those clamps kind of gave away why that's necessary. So let me turn the clamps back on, and I'll turn on the workbench there. So the clamps, what they do is, if you could imagine this tool going around and doing its cutting, having this much extra material off to the side allows for that spindle that's spinning 16,000 RPM with a very sharp object to stay clear away from the fixturing devices, which in this case is the clamp. I have seen situations where you could do various fixturing methods. Some people have been as brave as to take some really strong double-sided tape and literally tape the wood down to the table. I don't necessarily agree with that, and in this case I don't want to see that happen in the XPX Innovation Lab. The reason why I'm saying that is if for some reason the end mill is going around and it grabs a hold of that piece just right, it will actually peel it off the table and swing, like basically eject it from the table. And if you're standing right there, you could hurt yourself as well as hurt the equipment around the machine and anybody else that's around. So in this particular instance, by no means should anybody be using double-sided sticky tape to hold objects to the table. So what does that leave us? It leaves us with bar clamps. Obviously, we can get away with using these clamps to secure it to the table. Another method that I approve of in conjunction with the bar clamps is using long enough wood screws to go through your stock and bite into the actual surface, the spoil board. I've done that on many occasions, and if you closely inspect the surface board or the spoil board in the lab, you'll see little tiny holes all throughout the spoil board. And the reason why that's necessary is sometimes these clamps aren't holding onto an object enough to keep it from coming off. And we'll talk about the screws a little bit further down the road again when I talk about tabs and doing your contour cuts. But yeah, there are more than one way. There's more than one way to skin this cat. But fixturing is very important because we don't want the material flying off the bed. We want to hold the material as accurately flat as we possibly can. And yeah, I think I've beat that cat or that dead horse just enough. So we'll move forward. So once you've got your file basically designed and ready to go, we can go ahead and go back into the manufacturer tab on the right, or sorry, on the left. All right, I'm going to go ahead and unhide some of these components here. All right, so here we are back in our original view. So the first thing that we want to do is we want to create what's called a setup. There's good reasons to have one or more, well, you have to have one at least, but you could have more setups. So let's go ahead and create the first one. So we're going to come up here to the top and just under the milling, the word milling here, you'll see setup, and you're going to create a new setup. Now right from the start, because I have this 4 foot by 4 foot table showing, it's assuming that I want to mill the entire object, but that's actually not the case. So what you do on this tab here, you click stock, you have relative size box. This could work if you didn't know too much about your fixturing situation, or if you didn't know, like in some instances you might have a big object and you just go to the metal yard and you just buy this massive piece of stock. You could in theory just go ahead and use a measure, like a tape measure or my calipers, and get the actual size of your stock and put it in here. So you can change it to fixed size stock, and you can say, well, I've got something that's like let's just say 20 inches by 20 inches by 0.75 inches, and it disappeared somewhere. That would work for other situations, but we're just going to go ahead and just say from solid, and then that gives you the stock solid, so you can come in here and say, this is my stock solid. Now once you have that selected, obviously it's blue, there's something there's an additional step that you're gonna have to do. So in the setup tab, you have this milling or the model orientation, and then you have the origin, which is stock box point. You can do model origin, selected point, model box point. I'm just gonna leave it on stock box point, and I'm gonna select this tab, or this little point right here in the very corner. I'm going to say this is the origin of the stock. Alright. Now the X is going from left to right, the Y is going from front to back, and the Z is going up and down. Sometimes you might have a situation where it's flipped, like this. It's pointing in the wrong direction. So it's pointing away from your part, and if that's the case, all you have to do is just hit this red arrow and it should flip it to the more appropriate direction. I don't see any questions thus far in the comments. If you guys have questions, go ahead and type them into the chat on the right on that right side of the live stream. I have Doug monitoring Oh, looks like we're having an issue. Yeah, it's frozen for me too. Alright, let's see. Yeah, it did switch, didn't it? What a jerk. Okay. That should be better, guys. Yeah. Yeah, I just switched it back over. Should just take a second to switch back over to the main screen, I think. There we go. All right, how far back did it get frozen? Okay. So do you think it's worth going back and talking through the setup once more, or? Okay. Well, let's, I guess, cover the setup again. Just because we had a massive technical difficulty. So I just need I just need, whenever if we have that issue again, because I suspect it's just going to automatically switch over and I won't catch it right away. Okay. All right. So let's talk about this setup again. Okay. So if we rewind, and of course in the audio you guys might have heard it, but here we have this big piece of wood. Obviously we're going to try to get this piece of wood out of this one here. Alright, so let's create a setup again. We're going to go to the stock tab. We're going to change this from the relative size box to a from solid, and I'm going to select this as my solid. Alright, in the previous audio I had mentioned that if you went to the yard, or if you had like a custom sized piece of wood, you could literally measure out that piece of wood and use your calipers to get the depth and all that kind of stuff. But in this case, I'm modeling this under the pretense that I have a 3/4 inch, a perfect 0.75 inch piece of mahogany that I'm going to try to get this object out of. And you can see that we're running on a width of 2.7255 and 18.4846. So that gets us all set up on our this on picking the correct size stock. And then again in our setup, we need to select our model orientation. So right here you see this blue arrow shooting up, and the X shooting that way and the Y shooting that way. There's theoretically nothing wrong with leaving your orientation right here, but did it freeze again? Yeah. I'm not moving it while I'm talking. Okay. Anyway, like I was saying, you could, in theory, leave your model orientation or this stock box point directly in the center of your model. You could do that. But there's a couple things to note. One, if you ever lose, like if you have a malfunction in the middle of the part and you've already cut this circle out, you're not going to be able to get the exact position that you once were prior to starting your job. So I always recommend, and everyone has their isms, but I always recommend that you pick this back corner right here, this very back point, as your stock origin. Okay. I was saying in the video prior to it freezing up that if for some reason you see some craziness where it's all flipped like this, just hover over the arrowhead portion of this axis and just click that, and it should line up to where you see your X running along the one line here, and then the Y running along its appropriate axis here. Alright. The last thing that we're looking to do is tell the setup what model are we after. So I'm going to select this, and I'm going to say this is the model. This is what I'm trying to get out of this machine here. Why is it? That's what I want to get. Alright. So I should be able to turn off this body now. Okay. I'm going to hit OK. And now you see like the ghosted stock. It's there, but it's not. And then you see our actual model sticking out. Now I'm going to leave the clamps and all this stuff showing, because when we actually start doing the tool pass, you'll see a tool holder going around, and you'll see how much clearance we have. So let's start with the first. Let's start with the first tool path, and we might have an issue with this, or we may not. So as soon as you click a 2D adaptive path, a dialog box is going to pop up. You can select a tool. In this case, I've created a close to replica of the tool that we have on the machine. I think it's, no, I pulled it out, but we have a 1/2 inch flat end mill that is commonly used. It's like roughly a goldish color. So I'm going to go ahead and pick that. And for good measure, I'm going to go ahead and change our spindle speed to, oh man, I'm going to hit keys on the keyboard, and it's going to screw it all up. Let me do this real quick, just so that I don't have any issues. Okay. All right. Looks like we're still good. I have hotkeys set up on the streaming software, so if I push in a number, it's going to mess it all up. I can like inadvertently switch myself off. So I'm going to change the spindle speed to 16,900 RPM. And then I will change my ramp spindle speed. I'm going to keep that, let's just put 16,000 RPM there. The cutting feed rate is how fast the tool is going to traverse through the wood. 30 inches or 39 inches per minute is pretty slow for the wood. So if you're not going fast enough, that spindle, that end mill, is going to be moving really slow through the wood, and it's going to get hot, and it's going to take the sharp edge off the tool eventually. And you can kind of see where I was like trying to learn about, you know, feeds and speeds. I actually kind of scorched the bottom end of the end mill. So for now, I'm going to put it at 6 inches a minute. When you actually go to the machine and start trying to learn how to use the machine at the lab, I'll show you that you can manually increase your feed rate as you're cutting, and when you would do that. And there's like you have to develop an ear for it. So if it doesn't sound right, then chances are something isn't right. So you either need to speed up or slow down. But in this particular situation, I'm going to go ahead and leave it at 60 and 30 and 30. Now, where did I come up with this cutting feed rate, this lead out, and the ramp and the plunge? Okay, so I can't remember what exact video it was. I think it was NYCNC, but the guy, actually I'm going to change this to 40. The guy that was presenting the video basically said, you're going to have this rate, and then you'll divide that in half. So like for the ramp feed rate, we're going to do that 30. For the plunge feed rate, we're definitely going to go 30, because that's how fast the material dives down into the wood. And even this number is probably wrong. So if you're not in the XPX Innovation Lab and you're watching this, like because it's public and you want to try to learn how to use CAM, Lars Christensen and Winston Moy and NYCNC, those guys are way more clever at this than I am. And I'm basically trying to regurgitate a lot of the information they gave me onto you guys. So the lead in, lead outs, the ramps, the plunges, those things are definitely not 100% accurate. But for those of you that are going to be actually working on my machine in my lab, I'm going to show you why these numbers make sense when you're actually going to do your part. All right, so let's do the first pocket selection. So I'm just going to hold my mouse over this bottom circle here. You could do this one, but I hold it right here. And what that does is confines the tool path inside this circle. I'm going to switch to heights, go to the front view, and I want to talk about this real quick. All right, so you can see these 4 lines right here, and what they indicate is how high the spindle or how low the spindle is limited to. So the bottom height right now is chosen for selected contours, which is fine because if you remember, we picked the inside bottom circle. If you were to switch that to stock top, then it brings it up to the very top of our stock right here. You could say model bottom, which would also be pretty close to accurate, and there's no need for an offset. However, I say this with caution. This offset right here, let's say in the CAM world I have a 0.75 piece of stock, but in the real world, if you took a caliper and you were to measure it and it's like 0.7, right? So it's off by a little bit. You can actually give this an offset by saying 0.05 and hit tab. And what that would do is make it to where the bottom is just ever so slightly higher, so that whenever you're actually running the tool path, the end mill doesn't cut into the table. In this case, I'm just going to go ahead and leave it right at 0. Alright, the top height is going to be, that basically just, it's kind of intuitive. It basically means that the top height is set to the very top of our stock. Our retract height, for some reason this doesn't always populate the way that I want it to, but I'm going to go ahead and hit this drop down and say that this needs to go off of the top height. And we're going to offset this. We're going to offset this by 1 inch. So this is what the height would be when the spindle actually retracts. Now, it doesn't look like it's quite clearing the top of our clamps, so we could bring it up to 2 inches, and that would clear the top of our clamps. Our clearance height, you can just go off of retract height and you can add a little extra room for comfort. So you have a total of 3.75 inches of travel from your clearance height all the way down to the bottom of your model. Now, I should be able to hit, okay, we go to passes. There's a lot to talk about here. So if you end up falling asleep because I've just got like a voice made for radio, super monotone, I'm completely okay with that. I'm just going to keep talking, and hopefully you don't fall asleep, but in the event that you do, just come back and watch some of this stuff again. Alright, so if you were going to run a second tool path, or maybe you knew that you were going to change your bit, you would leave this checkbox right here, stock to leave. You would leave that checked. And what that's going to do is it's going to generate a tool path, but it's going to leave just a tiny amount of material left, so that when you go in there with the next tool bit, that tool bit is going to get to the actual dimensions of this pocket. In this case, I'm not interested in doing that, so I'm going to go ahead and untick stock to leave. Then I'm going to go to multiple depths. Okay, now our tool bit, you could in theory just go all the way down and hog it out, but you're really going to put a lot of stress on the machine, so and on the end mill for that matter. So it's best to make tinier step downs, and in this case I've got a step down of 0.39 inches. I feel okay with that. If you're a little less adventurous, or if you're cutting into something like aluminum, you definitely want to bring that down like quite a bit. So for example, when I was milling aluminum, I was doing a step down of 0.2 millimeters at a time, which is going to increase your job time tremendously, but we don't have a Haas in the lab yet. And I say keyword yet because I'm praying that Colonel Sneed reaches up to the clouds and the heavens that be, and they magically rain $70,000 on us and we can buy a really dope Haas. But for the time being, we don't have that, so depending on the material is going to be how aggressive you are when it comes to actually milling it down. Let's go ahead and leave, actually let's not leave that. Let's just, for funsies, let's say we're going to step down 0.25 every single time. It'll tell you like what it means. Now right here in this optimal load, keep in mind we're doing an adaptive tool path right now. We are not doing a pocket tool, and there's a big difference between the two. But the optimal load is going to be at the optimal load, there's going to be like this, what's the word I'm looking, it's how much the tool is engaging into the material. Right now, you can see that we're set at 0.2 inches, and from what I gather, the general rule of thumb is that the optimal load, or the step over, is going to be roughly half or a little less than half of your end mill. And if you remember, we have a 1/2 inch end mill. So if I right click this, I can hit edit expression, and it will show you right now that we would be looking at 40% of the tool diameter. So you could change this actually. And this is something I learned from Lars Christensen. So you can say, well, I want to be a little less aggressive, and I'm okay if it adds to the time of the tool path. So I'm going to go ahead and change this to 0.345 and hit OK. Your optimal load automatically updates right there. So let's hit OK, and let's watch it generate a toolpath for us. All right. So you can see the red arrow indicates that it's going to go down. The yellow line is basically going down, and then it'll do its thing, and then it comes up at some point, and it goes back over. It'll spiral back down, come all the way out this way, come back up, go back. It'll do that 3 times. So if I hit the simulation, you can turn your stock off, turn your stock on. I usually leave the stock on so I can really get a good idea of how the simulation is looking. Down here at the bottom, there's like a green bar that goes all the way across the window. It's probably not going to show up too well. Let me see, maybe I have to change. This might show it here. Yeah, so down here at the bottom, there's a green bar. If you see any little red marks in it, which you're going to see some in the next toolpath I do, it's trying to tell you that there's a collision. And there's some times to ignore that and sometimes not to ignore that. But in this case, this toolpath is giving us absolutely no issues with collisions. So I'm going to let it ride like that. All right, so let's go ahead and hit the play button, and you'll see the toolpath goes down, and it starts to get bigger and bigger. It goes around in a spiral. All right, let's slow that down just a smidge. I'm going to pause it. When it comes around the corner, pause it, here it comes. Alright, so again, this is like that optimal load I was telling you about. So right now it's taking 0.3, or so it's taking what was it, 0.345. So it's taking almost a half of it's taking basically like 34.5% into the cutting tool bit. Is that's how much it's engaged. So the less you engage, the more time obviously it's going to take to cut that particular part, but it's also going to cause less deflection on the end mill as it's going around. In deflection, I wish I had like a different pointer, but essentially deflection is the amount of pressure that's being applied against the end mill at this point right here. So as that comes around, then the deflection would be this way, and then this way, and then back on the back side. So that you can alleviate that by just changing your load on the end mill. I'm stepping down again, 1/4 of an inch every single time. So again, we're not being too terribly aggressive. So I'm just going to go ahead and keep going. And you can see here, like this represents the holder. So if you had the clamps bit down into this piece of wood right here, and this thing were to come swinging over, that holder would actually interfere with the clamps, which is why, like in this case, I've modeled it where the clamps are far enough away that it's not going to interfere with our cut at any time, especially when we do the contour cut, which is going to cut this piece out. So I'm going to go ahead and just speed that back up, let that go through and finish simulating. Alright, in the info you can look at like where its position would be, what the spindle speeds would be, what movement it's doing, like if it's rapiding, doing a rapid rather. Now the final tab on the right side here is the machining time and the machining distance and how many operations that we have running so far. We only have one operation and we have 0 tool changes at this point. This machining time is kind of not accurate. As a matter of fact, it's probably not. It's not going to be accurate, and here's why. When you take this file and you put it on the real machine in our lab, you remember how I was talking about how you can manually override the feed rate? Well, in this case, we would probably end up at a feed rate that's closer to 120 inches per minute going through this wood. And so that is probably going to reduce the machining time on that particular pocket by half. So instead of being 7 minutes and 48 seconds, it's probably going to be closer to 3 minutes. If you speed up or slow down that machining time, it's going to change. But anyway, we'll keep going. Alright, so I've closed that. We're back to our operation. Now let's try doing an adaptive toolpath again. This time I'm going to select this pocket right here, and this is going to show you, this is going to highlight an issue that I promised you I was going to discuss. So we still have our 1/2 inch flat end mill. We still have the values populated by the last command, 16.9, 60 inches a minute. The heights should be also legit, and they are. Our passes should be, they are not. So let's go ahead and do multiple depths again. I'm just going to leave that at 0.39. I'm going to leave that at half, or the 0.2 optimal load. That should be fine there. I'm going to go ahead and hit OK. It's going to generate, and I am going to simulate what that looks like. So it's going to bite down into it, and right off the cuff you'll probably already notice an issue or something that we're going to have to overcome. Just by looking at the corners, you can see that when you're using an end mill, you don't get your perfect 90-degree corners right here, right? Because the end mill is round. So geometry rules tell us that that's just never going to work out. But I'm going to go ahead and skip to the end. There's something that we can possibly do to overcome this, depending on how thick your material is and what kind of end mills you have. So in this case, something you could do is right click on this toolpath, the one that clearly doesn't get into those fine corners there, and you can do a create derived operation, 2D milling. You should be able to do, I think adaptive should work, but here you're going to change your tool bit. So I'm just going to create one real quick. Flat end mill, and this is going to be purely fictitious because there's no way in hell this exists, and if it does, it's very expensive. I'm going to say I have a 125 end mill, and I'm going to say that I have a shaft diameter of 0.5. And then I'm going to say that I have a shoulder length of 0.9. And, you know, since I'm just creating my own end mill here, I wish I can sell it for real. I'm going to say that I have a flute length of 0.8. I can tell you right now that this would be a very expensive bit. So I'm going to go ahead and hit OK. I've got an 1/8 inch flat. Geometry, I'm going to do rest machining, I believe. The tool diameter, the previously used tool diameter was 1/2 inch. Multiple depths should be fine. Optimal load, all that should be fine. Let's see if it cuts. So what we'll do is we'll do a simulation again. I'm going to step through and hit play. So you can see that like we shrunk that down and it gets a little bit closer to the exact corner of your project. Now you could, in theory, argue, well, coach, if I just went out and found an end mill that was a 32nd of an inch, I can get even more into that corner. And you're absolutely right. But I challenge you to find a 32nd of an inch end mill that long that can stand up to that kind of pressure and not pay NASA amounts of money on it. But anyway, that was just created just to basically show you the challenges of doing CNC type jobs on these kind of corners. Let's do a pocket now. 2D pocket. I'm going to select that as my geometry, and we're probably right off the bat we might see some collisions. Shouldn't have to mess with the heights. Those aren't accurate, but I'm more concerned about the collisions, because I think I'm going to get some on this. So let's hit OK. Alright, so now if I go to simulate, create a probably need to create a tool change in this, because if you really want to get down into those very small corners of the triangle, you would obviously go to your smaller bit, so 1/16 of an inch. If you could find such a mythological beast, or an eighth of an inch is probably more likely to happen. Let me speed that up. And this looks like it would take about 8 minutes, but obviously we'd be feeding way faster than that. There is no one in the shop. What do you mean by that, Josh? Please tell me you're not over at the lab trying to get in and run the CNC machine tonight. It's too late for that, bud. Alright, so if we do a simulation on our setup here, we can fast forward through all the tools, or all the paths. Alright, that looks good so far. Now it's time to cut the actual part out. So what could we use for that? That is going to be called a contour, 2D contour. So we select 2D contour. We're going to leave it on 1/2 inch flat. We're going to leave those feeds and speeds just right. I'm going to hit this as my geometry, this outside rectangle. Now in here you have a couple things that you can do. You can do tabs, which will generate these rectangular pieces in the wood, and what that'll do is secure the object to the remainder of that big piece of stock that we had on the table. He means there is a bit in the shop. Oh, yeah, but it's only 0.5 inches, dude. That bit that we have in the shop is only 0.5 inches. This piece that we're cutting out today is 0.75. So what'll end up happening is you'll be digging your holder, the chuck, the collet, into the wood, trying to get to the bottom of your stock. So that won't work. Now I do know that Amana Tools and I think Helical, yeah. Yes. Yeah. Okay. So I just had Doug chime in with a question in my ear because I've got him on the phone while I'm talking to you guys. So yeah, he's actually having to listen to me. So let's take a step back and let's talk about this red arrow. This red arrow, while not necessarily applicable in this case, this red arrow is basically going to contain your tool path to the geometry selected by this contour. So what happens if I click this? Well, in this case, you can see that it's going to move the tabs inward, but I'll come back to the red arrow on a pocket operation up here and explain why that or how to use that tool a little bit more accurately for a different type of operation. So getting back to the tabs, these little square boxes. These little square boxes are basically what's going to be sticking out of your material and holding it to the remainder of the stock. There are times when this is necessary and there are times when it's not necessary. So when it's necessary, if you are not willing to cut holes or drill screws down into this piece here to hold it down to the bed, those are necessary. And if you remember, we are not allowed to use double-sided sticky tape on Coach's Monster CNC machine because it might kill us. So we can leave the tabs in there. Now, you could change the tabs. You could make them longer. You can make more of them if you feel so inclined to do so. So you could just say, well, I want my tab widths to be 0.75. That way I have more material to like really hold it in. You can also say, I want my tab heights to be higher, like 0.25, and that'll make them thicker. What that really means is once you pull that entire piece of stock off the table, this object is still going to be stuck in there, and you have to use like a saw or a chisel to cut it out and release it from the stock. Whatever workflow works for you. I use tabs quite a bit to hold my pieces into the stock because I'm not afraid of going in there with like a little handsaw and cutting them down, and then I sand them smooth and you'd never even know they were there. You can increase or decrease the distance, so you can have like a ton of them, which would be absolutely unnecessary. So I'm just going to put that back at 3 inches. Actually, I'm going to go to like 4 inches. All right. So let's take a look at what that looks like in simulation. I probably didn't change the feed, so it's just going to go. Yeah, it just goes all the way right for the kill from the start. Normally your step downs wouldn't be so aggressive. Normally your step downs would be different. So you can always just go back and edit your tools or edit your passes. So I'm going to say, let's do multiple depths. And we're going to come down at 0.039. It's going to generate our tool path again. And as you can see, there's a lot more lines in it now. So it's going to take a little bit longer to cut out, but it's going to reduce the amount of stress put on the machine and the end mill by doing that. So let's go ahead and fast forward this to wicked fast. And you can see it goes around and around and around. Alright, so let's hide our tool paths. So when we zoom in here, this is exactly what is going to show, or this is exactly what is going to be left after you do your tool path. So you have these left, and you can just go in there with a saw and clip this down as close to the pieces you want, and then go back and do your sanding to just completely remove them all the way. Alright, so let's go back and address the question that Doug had. So I'm going to do a 2D adaptive clearing toolpath. I'm going to select this circle as my geometry. And there's our infamous red arrow. Now, as you can see, I selected the top of the geometry, not the bottom. So what happens when I click this? That means that this toolpath is literally going to try to cut all of this stuff around. So what happens when I generate this? It says empty toolpath. So let's go ahead and edit this so I can give you a better. I'm going to say that this is a negative offset of negative 0.125 inches. So it's going to actually bite down into the wood. Alright, or not. It's gonna make a fool out of me. How about we do the geometry thing again? Let's select this chain and then change that arrow and then hit OK. What do we get? Alright, this'll do just fine. So when I flip that arrow the other direction, now instead of trying to be inside of the circle, it's going to mill everything outside of the circle. And as soon as I hit play, you can clearly see that there's a massive issue of that toolpath. It's literally going to go right into the holding clamps, which would do two things: either A, break the clamp, or cut into it really nice, or destroy that bit and have pieces of metal just flying all over the place. So, did that answer your question? Are you still listening about the red arrow? Do I need to go in there and address that once more? I'm going to fast forward this so you can see the remaining circle and how silly it looks. Yeah, so as you can see, we totally annihilated the stock and now we have a circle. I'm going to go ahead and close this, and I'm going to change that back. I'm going to change that arrow back to the other way. And now you have the more appropriate toolpath right there. We don't need that because we've already got one. Alright, cool. So apparently I've answered the question. Alright. I can't think of too much more. Yes. Post-processing. Alright, so post-processing is going to be that last and final step before you can actually start cutting stuff out on the CNC mill. So how do you take these directions and get them into a file that you can put on a computer? It's a very, very simple question. But before I do that, I'm going to talk about technique. Let's see. I'm going to get rid of this one because that was just exploratory. Alright, so now we should have 3 tool paths. 1, 2, 3. I've deleted one too many. So let's do this. Yeah, 4. So 1, 2, 3. All right, and then finally 4. Okay. So you could hit, at this point, you could hit on your setup, you could go to this little button that says post process. And you're going to select here from personal, you're going to go to generic posts. And then there's a whole bunch of post processors here. If you had Haas, or if you had like a Chinese bot CNC on your desk, it's more than likely running something called TinyG. If you had a Tormach, if you had an Omax water jet, hint hint. If you had an other mill, which we do, we have another mill sitting on our on my electronics workbench. That particular machine I closely guard, so don't run any toolpaths on the other mill until you've talked to me first. But in this case, what we're really looking for is the CNC router parts. So it's just that one right there. And it's going to give you a program number. So you can just come in here and you could say Sean, the patent attorney job. And it's going to output that as a file. The document units, I've already put this in inches, so you can leave that alone. But if you didn't specify, you can come in here and put inches or millimeters. But I'm leaving it at document units because you can clearly see right here that the units are set in inches. And you could hit OK. I'm going to go ahead and hit open the NC in editor, and we'll see what happens with that. Hit OK. It's going to output the file. So for funsies, I'm just going to put this in a folder that I can quickly bring it up. Okay, so we just had a file pop up, and this is all the G code that runs that whole process all in one shot. All right, and G code is not necessarily something that's for the rook, although it's pretty good for someone to learn. So you can see right up here at the very top that our first tool, T1, is 5 inches. Its minimum travel is going to go down 0.75 inches, which would be good because we have a perfectly sized 0.75 inch piece of stock. In here, it's going to trigger a tool change, looking for tool number 1. So whenever you actually try to cycle start on the monster CNC machine in the lab, it's going to be like you're going to hit start, and it's going to pop up. It's going to say probably something like, "Hey bud, make sure you have the right tool." In this case, we'd already have the tool loaded because that's how I train you. So you can just hit go. It's going to make the spindle speed jump up to 16,000. It's going to sorry, didn't mean to cough in your ears. It's going to do some travel, so it's going to go to this position and this X and Y position. It's going to change its Z height, and it's going to plunge down, and then it's going to begin doing its cuts. Right here you can see that it changes the spindle speed up to 16.9, and then it goes on its merry way and starts doing a whole bunch of cutting. That's fine, but when you're brand new to the CNC world, I always advise you to break it down into multiple steps, and in this case we have 4 steps. So the very first one you'll do is you'll click on the actual toolpath and you hit process, and then you can just come in here and you can say step 1 job, and you would export that. Step 1 job. You can save this tap file to your hard drive, and then later on move it to a SD card or a thumb drive. Hit save. It opens it up, and this job is its own little job. Now, it's going to be far less lines of code, and it's going to alleviate what happens if you have a crash. So let's say, for example, you royally screw something up. By breaking it down into 4 separate jobs, you're only going to have to go back and repeat that particular step that you had a mishap on. So you would do this one, then you'd create a separate job for this one, separate job for that one, and a separate job for that one. You would take all 4 of those job files, those tap files, and you would load that onto your SD card, and then you would go to the CNC machine, where I'd be standing there watching like a hawk, and helping you get through the actual running of the tool pass. At some point, you will be so proficient with CNC, and if not probably way more proficient than I am, which is the hope, that I won't have to stand there and watch you like a hawk to make sure that you don't hurt yourself or hurt the machine. And if you're new to the shop, I do not want you running the CNC machine unsupervised for your first couple goes. The beauty of the Fusion 360 CAM is that you can simulate this as many times as you want. So if you go to the machine and you set your stock down and you clamp it down, but you're not sure of something, you can go back and watch the simulation to make sure that you haven't missed a step or that you haven't missed something. Finally, the last thing that I'm going to talk about, and this is more for running the machine. This is a little piece of knowledge that I picked up on. So what'll end up happening when you do your setup is you'll clamp your stock down. I'm going to hide this body. You're going to clamp your stock down, and you're only going to put on these 3 clamps first. These ones in the back corner. You're going to put those on first. You're going to leave this one off. And what will end up happening is you're going to drive your CNC end mill over to this back corner, and you're going to put the center of that bit right here on this X and Y axis. And you're going to get the Z down to where you just barely drag a piece of paper underneath it. You're going to zero the machine, and then you're going to put the clamp back on. So you zero the machine and you raise the end mill up high enough that it clears all the clamps and everything. So you could arbitrarily just bring it up like 4 inches, just so it's way up in the sky. And then you put your clamp back on. And when you hit start, it'll automatically traverse over to this thing here and then drop down and start doing your cuts. If you leave the tool bit right here on this very, very back corner, it's going to turn the spindle on and it's going to whip across and crash right into this clamp and cause a catastrophe, and the world falls apart, the lab burns down in flames, and coach gets fired and everything's bad, right? So I'm just trying to drive the point home that you leave the clamp off first, set your zero, raise the tool way up, get it way up out of the way, and then put your clamp on, and then you can hit cycle start and it'll come over here and do its thing. If for some reason you have a massive issue, or maybe you changed your tool bit to a smaller one, you would do the same thing. You would bring it over here, remove the clamp, lower it down to this thing, this corner here, get your Z, get your X, get your Y, raise it way back up, get it way out of the way, and then put your clamp back on, and then resume your job with the smaller tool bit. So that's that for this particular job, for this particular getting started. I suspect in the near future that someone will have a more complex job that involves doing some 3D tool paths, at which point I will be more than happy to create another live stream that you guys can watch, and hopefully give you guys some good information on doing that. Again, I am not a professional CNC guy. I'm just, I would say, a novice at best. there are people that are way smarter at this. So if you're on the YouTube machines and you want to learn a little bit more, I suggest you look at Lars Christensen and his CAM toolpaths video tutorials. There's also Winston Moy, who is a wizard at this stuff. Only downside to his videos is that he talks pretty fast, and he's assuming, I guess, that you have already a level of proficiency in CNC. But I always like to cross-reference Winston Moy and Lars Christensen whenever I'm looking at CAM videos. And finally, NYCNC in the earlier days, back before he got super famous and super rich, because now all he does is work on machines that are like pro grade stuff, and you're only going to see like the Haas or the Tormach. You won't see machines like this, but he does nevertheless have some pretty good videos on CAM for beginners back in the early days, and I think that dates around 2015, 2016 time frame. More of his recent stuff is just going to be sort of way above your pay grade at this point, and definitely way beyond the capacities of the lab, because we do not have the pro grade stuff. So with that being said, thanks for tuning in. If you've managed to survive my incredibly monotone voice, good for you. If you didn't survive my monotone voice, or your wife was pulling on your shirt and saying get away from the computer, definitely come back and watch this. We're gonna have it public, so you can watch it as many times as you need, and yeah, we'll go from there. This is Coach signing out from XPX Innovation Lab. I hope you got some good information from watching this, and yeah, until next time, I'm signing out. Have a good night.